Hello, and welcome to today's lesson on the ideal transformer equation. We'll begin today's lesson by understanding the concept of an ideal transformer, which assumes no energy losses and 100% efficiency. Next, we will introduce the equation which describes ideal transformers. Finally, we will work through examples of applying this equation to consolidate your knowledge. So far, you are familiar with the basic concepts of transformers, including what they are, the differences between step-up and step-down transformers, and the standard transformer equation. This foundation enables us to delve deeper into the ideal transformer equation. By understanding this concept, we advance our comprehension of how electrical energy is transferred efficiently in transformers, highlighting the principles of energy conservation and power consistency. Let's get started. An ideal transformer is a theoretical device that efficiently transfers electrical power from one circuit to another without any energy losses. While real-life transformers do experience some energy losses due to heat, sound, or electromagnetic radiation, the ideal transformer assumes 100% efficiency. That means all the electrical power input into the primary coil is transferred to the secondary coil. This assumption lets us simplify calculations, making it easier to understand the core principles. For an ideal transformer, the power input into the primary coil equals the power output from the secondary coil. Therefore, input power equals output power. We know from the electricity unit that power equals voltage times current. By substituting this into the transformer relationship, we get Vp times Ip equals Vs times Is, where Vp is voltage in the primary coil, Ip is current in the primary coil, Vs is voltage in the secondary coil, and Is is current in the secondary coil. Let's work through an example to understand how to use this equation. Suppose you need a transformer to provide 500 watts of power at 100 volts on the secondary side, with a primary voltage of 250 volts. We need to find the current drawn from the primary input supply. Firstly, identify the given values. Secondary power, PS, equals 500 watts secondary voltage, Vs equals 100 volts, primary voltage, Vp, equals 250 volts, and the primary current, Ip, is unknown. Now calculate the secondary current. We know primary power equals secondary power, and primary power equals Vp times Ip. Using the given values, 250 volts times Ip equals 500 watts. Ip equals 500 watts over 250 volts. Ip equals 2A. So the primary current drawn from the input supply is 2 amps. In another example, suppose you have an ideal transformer with 400 turns on the primary coil and 100 turns on the secondary coil. The input voltage is 240 volts and the primary current is 2A. We need to find the current in the secondary coil. Firstly, identify the given values. The number of primary turns, Np, equals 400. Number of secondary turns, Ns, equals 100. Primary voltage, Vp, equals 240 V. Primary current, Ip, equals 2A. Secondary voltage, Vs, and secondary current, Is, are unknown. Now apply the transformer equation to find the secondary voltage. Vs over Vp equals Ns over Np. Vs over 240V equals 100 over 400. Vs equals 0.25 times 240V. So secondary voltage is 60 volts. Next, use the ideal transformer equation to find the secondary current. Vp times Ip equals Vs times Is. 240V times 2A equals 60V times Is. Is equals 240V times 2A over 60V. Is equals 480A over 60V. Thus, the secondary current is 8A. In today's lesson, we delved into the ideal transformer equation and its significance in understanding transformer functionality. We defined an ideal transformer as a device that operates with 100% efficiency, where all the electrical power input is transferred to the secondary coil. This principle allowed us to focus on the ideal transformer equation. By mastering these concepts, we reinforced our comprehension of energy conservation and power consistency in electrical systems. Understanding these principles provides a solid foundation for further studies in magnetism and electromagnetism. Watch the rest of the GCSE physics course at Sophos Education.